Welcome to another podcast. In this episode, we're going to be taking a look at something called a linear approximation. This is another application of derivatives, and specifically an application of tangent lines. We've been spending most of the semester learning how to calculate derivatives of various functions, and one of the main reasons for that was so that we could calculate the equation of a tangent line. And the question at this point is, well, what good is that? What does the tangent line help us do? And this is a really good example of the benefit of the tangent line. The tangent line allows us to do what's called linearize the function, which allows us to approximate things via something called a linear approximation. So, the main thing that I want you to take away from this video is that when we talk about the tangent line to the curve f of x at the point x equal to a, this is, in an applied sense, the same thing as the linearization. So this is a new word for us. The linearization of the function f of x at the point x equal to a. In other words, it's kind of like saying that near the point of tangency, if you zoom in far enough, the function looks almost like a line, and the line it almost looks like is the tangent line. So if I want to know what's going on near a point of tangency, then I can just look at the tangent line and it gives me the information rather than the actual function. And sometimes that is very beneficial. So let's make this a little bit more precise. Specifically looking at the tangent line to the curve, we know that our tangent line formula is f of a plus f prime of a x minus a, and we're going to call the linearization function L of x. And so this is called a first order approximation because it uses a first derivative. So this is a first order approximation of the function f of x. In other words, we think of the function L of x as being approximately, so the function L of x is approximately the function f of x near the point x equal to a. In other words, we might trade a really complicated function for a much simpler line, and they basically behave the same near that point. So let's look at an example of this. Go ahead and calculate this. Let's let y be equal to the square root of 1 plus x, and we're going to look at this at the point x equal to 0. So I want to know, what is the linearization of this function at the point x equal to 0? Well, that involves us having to find the derivative. So the derivative of this function is 1 half. So remember, this is 1 plus x to the 1 half. So it's 1 half 1 plus x to the negative 1 half, which is just this root. And at x equal to 0, f prime at 0 is 1 over 2 square root 1 plus 0, or just 1 half. So our formula for the linearization is basically the tangent line formula. It's the function at 0 times the derivative at 0, x minus 0. And the function at 0 is the square root of 1 plus 0, or just 1. The derivative we've calculated is 1 half, and x minus 0 is just x. So for this particular problem, this is the linearization. What that means is, at the point 0, we can replace this function with this line, and they are essentially the same near x equal to 0. So the follow-up question to this is, suppose we wanted to calculate the square root of 1.05 and did not have a calculator. Could we use L of x instead? And the answer to that is yes, and that's the whole point of this. Now, here's the issue. The answer is yes, but we might expect error. And in fact, we should expect error. All right, well, let's give it a whirl. If you look at the function f of x equals square root of 1 plus x, then the square root of 1.05 is really 1 plus 0.05, so this is the value of f at 0.05. So I want to compare the value of the function at 0.05 with the value of the approximation at 0.05. So the linear approximation L at 0.05 would give me 1 plus 1/2 times 0.05, which that's a value of 1.025. And the question is, how good did we do? Well, the question of how good did we do is a question of what is the absolute error. And you calculate absolute error by looking at the difference between your approximation and the actual value, which is the function. So here, the approximation gives us 1.025, and the actual function is the square root of 1.05, which, if you plug into a calculator, square root of 1.05 is approximately 1.0247. So this is equal to, or less than or equal to, I should say, 0.001. In other words, the first place where we make an error is in the third position, and because of that, we have a very small error for this particular problem. The third position is where they first differ, so that's the first place where error is introduced, and they're one apart in that third position. So this is called the absolute error. The absolute error is less than 1/1000th of a point. So that's pretty good, considering that we didn't need a calculator to actually calculate this value. It's pretty good that we can get within 1/1000th. Now, what makes this possible is that we're staying close to the point that we linearized. So we linearized the function near the point 0, and we're trying to give an approximation at 0.05, which is pretty close to 0. One of the big ideas here, and one of the more important things to get out of this video is, as you move away from the center, and this is the center point for this example, the function L of x will have a larger absolute error. In other words, that linearization is only good near 0. If you try to get too far away from it, then you're going to introduce more error into your approximation. Specifically, let's take a look at this for a couple of different examples. I want to start off with, so we're going to fill in this table. Let's talk about the headings of the table. We're going to look at a couple of different values of x. We're going to look at x at 0. We're also going to look at x at really close to it, 5/1000ths. We're going to look at x at 0.05, which we've done down here. And then we're going to look at x at 2/10ths, which is pretty far away compared to 5/1000ths and 5/100ths. So I need to calculate the function value. The function here is the square root of 1 plus x, and so here the square root of 1 plus 0 is just 1. Here it's the square root of 1.005, which that's approximately equal to this value. Here it's the square root of 1.05, which we've said below is approximately equal to 1.0247. And then 0.2 is the square root of 1.2 is the function at that point. And this is approximately equal to 1.09545. So these are our function values at each of these 4 points. Now the question is, how does this compare to my linearization of those values at those points? So 1 plus 1/2 x, remember that's the linearization. So rather than use the square root function, I'm going to use this linear function instead to approximate. And at 0, 1 plus 1/2 0 equals 1. Notice that they coincide. In other words, your approximation is perfect. You're going to be perfect at the center point always, because it's designed so that the tangent point and the function coincide at the point of tangency, so there's not going to be any difference between them there. That's the only point where they touch. All right, moving forward, let's calculate it for this x value. So the linearization here is this, which it gives a value of 1.0025. And then we calculated this one below. This one's 1.025. And then the linearization at 0.2 or 2/10 is 1.1. So here is our linearization or our approximation at each of these points. Next, we calculate what's called the absolute error. So this is exactly what we did below. The absolute error is the difference between this column and this column, so the difference between these two numbers. So 1 minus 1, an absolute value is 0, so this goes back to what I'm saying. You don't commit any error, you're perfect at the center point. The difference here is 1.002496 minus 1.0025, and you see here that the first time that they disagree is in the 4th decimal place, and so this is less than or equal to 10 to the negative 4th in terms of accuracy. So it's within 1/10,000th of a point of accuracy. So very close accuracy wise to the actual value of the function is this linearization at that point. We calculated the absolute value here below. For this one it was 10 to the negative 3. And then for this one, we're looking at the difference between 1.09545 and 1.1. And you can see that these two are actually not all that close at all. The difference here is less than or equal to 1/100th. So they're about 100th apart if you subtract those two. What I want you to notice here is looking at each of these values, it clearly demonstrates the principle that is described here, and that is as you move away from the center point. So I'm moving away from the center point. As I move away, the absolute error gets larger. So from 1/10,000th to 1/1000th to 1/100th, and as I continue to move further and further away from 0, these numbers will get bigger and bigger. So there, at some point there's a stopping point where it's just not worth it to approximate things at 0 with this function if you get too far out. Finally, this last column here is something we haven't talked about yet, and that's called the relative error. So the relative error, we typically think of this as a percent error, meaning that we think of, okay, how big is this absolute error compared to the actual size of the function? Because if the error is big and the function is small at that point, then that's going to be a really large error. So here the relative error is defined as the absolute error divided by the function. So it would be column 4. So if we're keeping track, this is column 1, column 2, column 3, column 4, column 5. So column 5 is really just the column 4 divided by column 2. So here we get 0 divided by 1, which equals 0% error, which makes sense. There's no error for that particular one. For this next one, we get 1.002496, and we get 10 to the negative 4th divided by that value. So we get 10 to the negative 4th divided by 1.002496. And so that ends up being approximately 4 times 10 to the negative 6. So if we think of this as a percentage, this is around 0.004%. So that's the error, the relative error for that case. For the 0.05, it would be 10 to the negative 3 divided by 1.0247. And that is approximately 0.029%. And then finally for this last one we get 10 to the negative 2 divided by 1.09545, and that is approximately 0.4%. So the relative error there of 0.4% is pretty, it's getting up to where we might not want to consider using that. There's a big enough error there that we might want to try something else. All right, so this is the idea behind approximating, which is what the tangent line does, and it's sort of the first step in a much larger work. Specifically, you'll carry on this concept into Calculus 2, and instead of looking at first order approximations like we do here, you'll look at second order, third order, fourth order, and in general nth order approximations via something called a Taylor series. And so we're really just starting to head in that general direction, and you can see the benefit of it. We can take an approximation of a function near a point and use the simpler thing to give information near that point rather than use the more complicated thing, which is usually the function itself. All right, thank you for watching.